The first figure shows the access point on the web of a deployed Proxmox server, with the response to a GET service concerning the bridges put in place in the Proxmox instance. The second figure shows the API of Proxmox, with all services that can be called. C platform provides then an interesting potential of being able to couple integrated business, information and ICT monitoring of events and to automate some reconfiguration based on complex event processing, addressing all the layer of the information system. Having a collaborative platform used for operating a dynamic manufacturing network is not sufficient if not possible to make it evolving easily. It implies to have, in addition to the operational platform, design and development platforms with associated shared practices in order to make it evolve properly, maintaining the quality of the platform, such as scalability, interoperability, agility, flexibility and so on. For maintainability and low cost of evolution, having appropriate studios for deploying business logic on top of the execution platform constituted by the infrastructure of the living lab is crucial. It is why some studios were identified, which facilitate design, development, deployment and configuration of software components artifacts. The DMN Studio is currently composed of two implementation platforms. The first, based on NetBeans, it is dedicated to the development of web services server or clients which can be accessed through the Enterprise Service Bus, and is the most effective for usage of OpenESB. The second is dedicated to development of portlets, and is based on Eclipse and Vaadin, which was identified as the easier way for developers to produce easily and fast compliant portlets. In addition, all the testing environments are associated. Aeronautic Living Lab collected configuration to be used and distributed as best practices for efficiency among development teams, which can be involved in the enrichment of the collaborative platform. The Autonomic Service Bus is an enterprise service bus based on web services standards defined by World Wide Web Consortium, such as Web Service Description Language or Simple Object Access Protocol, or Java community standards such as Java Business Integration. It is realized by OpenESB and a set of plugins for data transformation, file transportation and composition of web services, based on the business process execution language. It is extended with a quality of service manager allowing to monitor quality of service for a node of the network, machine, application. The manager should notify when is required a need for automated recovery action, such as load balancing with new server, or semi-automated recovery action with human in the loop. Together with the Enterprise Service Bus, the Quality of Service Manager realized the Autonomic Service Bus. The Autonomic Service Bus is also extended by a Security Policy Manager, based on XACML, and allowing to deal with heterogeneous web services security policies for the interconnected applications and enterprise. This service bus component is used in order to ensure the interconnection of partners' legacy applications to the PLM hub in order to support their interaction with the C platform as a mediator. The Autonomic Service Bus allows to address the Imagine integration platform non-functional requirements, in particular, the high number of concurrent communications, which relates to global scalability of the ESB and services when traffic increases. The interconnected systems with different quality of services expectations, in relation to the management and satisfaction of the non-functional requirements. And the high dynamicity of the context, related to the complexity of scalability and quality of services management in a manual way. The Autonomic Service Bus provides a smart solution to manage the performance of the Living Lab IT infrastructure. The ASB is able to manage the Enterprise Service Bus mediation component, in particular in order to warrant integration, interoperability and quality of services requirements in an autonomic way by providing self-management capabilities. The Autonomic Service Bus follows the autonomic computing architecture presented in the figure. In this architecture, a closed management loop providing monitoring, analysis, planning and executing functionalities is implemented based on a common knowledge base. The self-management functionalities allow to observe the ESB using the sensor interface and to apply adaptive actions using the effector interface. The adaptive actions can be related to the virtual or physical resources of the infrastructure. The Autonomic Service Bus relies on the autonomic computing maturity levels, starting from a manual management of the OpenESB component until the self-configuration of the whole system. This figure illustrates how the self-configuration of the CPU threads allocated to the ESB can have an impact on the response time of the requests or responses of the distributed services managed in the platform. This figure illustrates how the self-configuration of the number of CPUs improves the response time of the requested distributed services managed in the Living Lab platform. Access control component addresses many problems including the role definition and delegation following to the roles-based access control model, the policy administration, the interoperability among partners, the policy deployment, and the rules conflict management. The figure illustrates the access control interaction between the different component based on the XACML standard. The policy enforcement points are designed based on the following processes. The PEP intercepts users' access request to a resource. Then it transfers the request details to a policy decision point. Pos equal 1, 5 and finally it enforces the decision of the PDP. Pos equal 1, 5 the PEP is implemented as BPEL process. The policy decision point, PDP, evaluates the authorization decisions. It is implemented as a web service. This figure illustrates the use of editors provided by OpenESB development environment. This approach is used to implement the autonomic access control components. This figure illustrates the use of the UX-ACML editor to manage access control policies. A graphic policy definition editor implemented in Java language and based on the XACML standard. This figure illustrates the use of specific web-based interface to download or upload policies from or to the repository. As a conclusion, this training allowed to clarify business motivation and non-functional requirements of the platform for the Aeronautic Living Lab. It also illustrated how the functional component and the implementation, being solution on the shelves or solution developed by the Living Lab partners, were put in place, with the presentation for each solution components of the usage according the processes of the DMN methodology. For all these components, dedicated documentation and cookbooks are available allowing to really master them. This tutorial was made to help DMN designer and DMN manager to understand how the aeronautic implementation of the AI platform should be used, but also in order, allowing information system architects and information and communication technologies architects to be able to maintain and make evolve the infrastructure of the Living Lab, highlighting the principles applied to obtain an interoperable and flexible solution for secured collaboration.